All right, so we're still looking at Taylor and Maclaurin polynomials, so we have another example of that. And then we'll talk about the error involved with calculating using a Taylor and Maclaurin polynomial. It's usually pretty small. It's a very, very small error, and that error is sometimes called the Lagrange error. Or Lagrange, I guess he's French. So use a fourth Maclaurin polynomial, so fourth degree. Maclaurin means we're centered at 0 to approximate the value of ln of 1.1. We already made a polynomial for ln centered at 0, or no, we made one centered at 1. Centering at 0 is tough. So what we do is instead of saying, ln of x is our function, we can use ln of x plus 1 as our function, or 1 plus x is how they write it, but it doesn't matter which way you put the x and the 1 in there. And then we can center it at 0, and then we're really close. Then our x would only be 0.1 when we want to plug in later. All right? So that's a nice little trick we can do if we're farther away, like 1.1. That's pretty far away from 0 where we're centered. So we can change the function, or think of the function as ln of 1 plus x, or x plus 1, and then center it at 0, and then plug in 0.1, which is much closer. All right, but first we need some derivatives. So it looks like we're going with g of x is ln of 1 plus x. So then g prime would be 1 over that, or 1 plus x to the negative 1. G double prime, bring down the negative 1, we get negative 1. I want to write the x first. 1 plus x to the negative 2. And third derivative, we need to go to the fourth. Bring down the negative 2, we're going to get positive 2. 1 plus x to the negative 3. And fourth derivative, bring down the negative 3, we get negative 6, like that, to the negative fourth. So that means g of 0, and yeah, we are plugging in 0 because we are doing Maclaurin. We're centered at 0. Plug in 0, we get ln of 1, which is 0. If we do g prime of 0, we plug in 0 here, we're going to get 1. G double prime of 0, we're going to get negative 1. G triple prime of 0, we get 2. And the fourth derivative at 0 is negative 6. All right, so we've got our coefficients here. So now we can make our Maclaurin polynomial of degree 4. So we have 0 plus 1 times x over 1 factorial plus negative 1 times x squared over 2 factorial plus 2 over x cubed over 3 factorial plus negative 6 x to the fourth over 4 factorial. All right, and we can simplify that sum if we want. All right, that would just be x minus x squared over 2 factorial. And let's see, the 2 is going to cancel here. Actually, that 2 factorial is really just 2 there. Plus x cubed over 3 minus x to the fourth over 4. All right, the 6 is going to cancel out with the 3 and the 2 there. So we get that as our fourth degree polynomial. So it looks like the next one would be plus x to the fifth over 5, and then minus x to the sixth over 6, and so on. And now we want to plug in 0.1. So 0.1, we're going to get 0.1 minus 0.1 squared over 2 plus 0.1 cubed over 3 minus 0.1 to the fourth over 4. And we can just throw that in our calculator. All right. Now, in the olden days, it was easier to calculate these polynomial type things than it was to calculate natural logs. And that's actually how they came up with the values for natural logs. They would make tables of all these values. So 0.1 minus 0.1 squared divided by 2. Actually, we already have this here, don't we? Or something similar, not quite. Plus 0.1 cubed to the third over 3 minus 0.1 raised to the fourth divided by 4. And we get 0.0953. All right, and then let's see, how does that actually compare to the ln of 1.1? So the natural log of 1.1 Oh, look at that. They're all the way the same, all the way out to the 3. So they're exactly the same to 4 decimal places. And if we rounded to 5, they'd be the same to 5 decimal places too. So that's a pretty good estimate there with just the 4th degree term. All right, so what's the remainder? So what are we left over with? So I know we're approximating these and they're close, but they're not quite exactly right. So that's the polynomial value plus some other value here, and this other value is called the remainder. So we could really just subtract the function value minus the polynomial value, and that would give us the remainder value, right? And that is the error associated with this approximation. That's how far it's off by. So often we just take the absolute value of it to make that error a positive number. All right, so the way we find that error. So the error associated with an nth degree Taylor polynomial or Maclaurin polynomial is that. So it's the derivative, the next derivative. So this is n. Notice this is n plus 1. It's the next term, basically. So we already have the n degree polynomial. We look at the n plus 1 term at some value c, or z, I guess, z, over the coefficient, the n plus 1 factorial, then x minus c to the n plus 1. All right, now, what is the z thing? Well, the z is just the value that maximizes the derivative. All right, usually we say between x and c, but oftentimes we'll just say what's ever easiest. Sometimes we'll just use 1. All right, so one useful consequence is that this, the error, is always less than the absolute value of x plus 1 to the n over n plus 1 factorial times the maximum value of the derivative of z. All right, so that's what we end up getting from that. All right, so for example, we have a third Maclaurin polynomial, so p sub 3 for sine. All right, we calculated this, something similar to this before. It's x minus x to the third over 3 factorial. All right, we use Taylor's approximation for sine of 0.1 by the polynomial at 0.1, and we want to know how accurate is it. So if we plug in, well, we're going to have this extra remainder here, and this remainder term would be that, the next term, right, the 4th derivative at some function value z over 4 factorial times x to the 4th. All right, where z should be between 0 and 1. So if we plug in, sine of 0.1 should be approximately that polynomial value, which works out to this 0.099833. That's the polynomial value. This is p sub 3 of 0.1. All right. The 4th derivative of sine is just sine. So that means this error term, this remainder, can be found as follows. So the remainder at 0.1 is sine of z for some z value times 0.1 to the 4th over 4 factorial. All right, now the maximum value of sine of z anywhere is just 1. So we're just going to use that, 1. I know that might not be the maximum value between 0 and 0.1, because sine starts at 0 and goes up, but we can just use 1. I mean, it'd just be a decimal otherwise. All right, so if we just use 1, this to the 4th over 4 factorial gives us that's our error. So we're only off by 0.000004. That's a pretty good estimate. All right, so that means sine of 0.1 could be as much as that. All right, it's somewhere between those two values. All right, that's just adding in the 0.000004. All right, so that's how Taylor and Maclaurin polynomials work, and that's the end of this section. Most of the error stuff won't show up, guys. It's mostly just Taylor and Maclaurin polynomials is the important stuff here.